Marta Volonteri, to have Marta Volonteri today with us. I have known Marta since my days in Paris. She was always the super busy person working on the foremost black holes, how the first black holes formed. It was black hole seeds at the time, right? The focus of the research. But she has done a lot of galaxy evolution, formation of the black holes, accretion, and now gravitational waves. Now I learn gravitational waves since a long time. So Marta got her PhD from Milan, and then, correct me if I miss something, you moved to Santa Cruz, then to Cambridge, and then to Michigan, where she was tenured as an assistant professor and an associate professor. And then she moved to IAP in Paris, where she had a big team with an ERC. And this is the part that I knew best. I have heard her given very nice speeches, so I invited her today. So we're very pleased to have you. We don't have, since we have the virtual colloquia, we have nice people like you. Before that was quite isolated, so we're very happy to have people like you with us. So thanks for the talk you're about to give us, and the floor is yours.
Thank you very much. It's really a pleasure to be here virtually as well. To be honest, yes, I'm always super busy. And this semester has been a nightmare with travel because all of 2020 and 2021 have been compressed in the last 6 months. So I really appreciate that you have given me the opportunity to give this talk virtually. So today I will talk about some work that I've been doing in the last few years, focusing on massive black hole pairs and binaries in the cosmos. The final goal is to work out properties of massive black hole mergers for LISA, but on the way there, we're mostly focusing on AGN as tracers of binary black holes. So as a bit of introduction, first, when I talk about massive black holes, what do I refer to? Usually when we talk about black holes in the universe, we talk about two different families. The low mass stellar mass black holes, we know that they are formed at the end of massive stars. And here there is a collection of a few sources, both detected electromagnetically in purple and with gravitational waves by LIGO Virgo in blue. The masses are from a couple of solar masses, have been based, at least in principle, on the physics of neutron stars, up to several tens of solar masses, as shown here. But then there are the massive black holes that I work on. These are really of a different class in some sense, because their masses, their observed masses, go from a few, about 10,000 solar masses, to more than 10 billion solar masses. The most famous massive black hole is our own, Sagittarius A star at the center of the Milky Way. It has a mass of 4 million solar masses. And the high mass end, we also have very good knowledge of the black hole in the galaxy M87. You see here, it's a nice elliptical at the center of the Virgo cluster. From far away, you see a jet, and then close in, you can see the photon ring. So the presence of this jet is telling us that the black hole in M87 is active. In fact, in the universe, we see AGN, active galactic nuclei, and quasars that are powered by massive black holes. And as I mentioned, usually they live in the centers of galaxies. Those in nearby galaxies have been studied in more detail, but through the presence of AGN and quasars, we can trace their presence through very early cosmic times. And during this talk, I will relax some of these assumptions on the properties of massive black holes and show you, for instance, that not all of them are expected to live in galaxy centers. So I mentioned active black holes. This is my favorite quasar, 3C273. It's my favorite because it was the first one discovered in 1963 by Martin Schmidt. And so this is how the whole story of massive black holes in the universe started, really. They can be as luminous as entire galaxies, 10 to the 11, 10 to 13, so our luminosity is even higher. But the size of the emitting region is about the size of the solar system. So the only objects that can produce this type of power from such a compact region are accreting black holes with masses of millions to billions of solar masses. And I mention accreting because the light is produced as material, usually gas, swirls towards a black hole, forms an accretion disk that radiates at several wavelengths. And including jets, the production of energy can go from radio to gamma rays. At the other end of the spectrum of black holes, we have what we call quiescent massive black holes. These are black holes that are very, very faint. For instance, our own black hole has a mass of 4 million solar masses, but the typical luminosity of Sagittarius A star is only about 10 to the 34 arcs per second, which is comparable to the luminosity of the sun. So from quasars, we have single objects that are as luminous as entire galaxies. And for quiescent black holes, we have black holes of similar mass, but that only are as luminous as a single star. And this is an image, a composite image, where you can see that at the location of Sagittarius A star, really there is no bright source that we can detect, for instance, in infrared. Over the years, especially starting in the mid-90s, we have collected information on the presence of these massive black holes in many nearby galaxies. And what has been discovered, again, starting from the mid-90s to the beginning of 2000, is that the masses of these black holes correlate with the properties of the host galaxy. The most famous relation is called M-sigma relation, a correlation between the black hole mass and the velocity dispersion of the host galaxy. I will not focus in particular on these correlations here, and instead of showing M-sigma relation, I show here the relationship between black hole mass and stellar mass. The reason is simply that the stellar mass is very easy to measure, both in simulations and observations, so we can make a one-to-one comparison. In fact, in this figure, I show both observed massive black holes. These are shown with the green triangles and the yellow contours. These are mostly quiescent or quiescent black holes or faint AGN. You see here that there is a correlation, although not very tight, between black hole mass and stellar mass. But in general, what you can think is that the black hole mass scales with the galaxy mass with a factor of about 10 to the minus 3, 10 to the minus 4. At the bottom line is that big black holes live in big galaxies, small black holes in small galaxies. And this correlation is expected to have been established over cosmic time scale, so in the last 10 billion years. Other observations are also shown in blue here. Now, if we move to theory to simulations, this is shown with orange and the gray shaded area. We also reproduce part of this correlation in simulations, really having black holes evolve over cosmic time with their host galaxies. Here, what I wanted mostly to show is that in terms of observations in particular, you see that most of the information is for the most massive black holes, where say something about above 1 million solar masses or so, really the bulk of the information is 10 to the 7 and higher. Although when we go to very massive black holes in very massive galaxies, they start to become rare and so harder to find. But these blue points also show that we are building information, we are filling this diagram also at the low mass end, which is very important if we want to understand the establishment of black holes in galaxies, feedback processes, and so on and so forth. So how can we try to fill this mass plane? And here I will add some extra complexity by adding also the redshift plane, so a plane of redshift and mass. In fact, we don't only want to measure black hole masses or detect black holes in the universe, we also want to study their evolution over cosmic time. And you see here on the right-hand side, we have some pivotal times in the formation of the universe, from inflation, first stars, first black holes, first galaxies, all the way to today. On this figure instead, you see these two shaded areas. These represent the reach of gravitational wave observatories. One is LISA. It's an ESA NASA partnership with the majority to ESA, planned for the second half of 2030. And as you see here, it can detect black holes with masses about 10 to the 5 solar masses at redshift 20 and beyond. ET stands for Einstein telescope. This is a ground-based gravitational wave detector. And in this case, it's aimed at detecting smaller mass black holes. This is accompanied by a really wealth of electromagnetic observations, we call telescopes and satellites, observing in a variety of wavelengths, from X-rays to radio, infrared, optical. And so with this combination of multi-wavelength observations plus gravitational waves, we have a multi-messenger view that really can inform us on the evolution of black holes from very, very early times. You see here about 200 million years after the Big Bang, all the way to today. So the goal of my recent, but also past work, but in particular, I will focus here on very recent work, is really to try to build the theoretical framework to interpret observations, upcoming observations, and also to make specific diagnostics that can help us study the evolution of massive black holes. Ouch, sorry. Let's try again. Okay, so this movie shows a cosmological simulation where we have the formation of galaxies and black holes as well. The blue background is dark matter. Within the blue background, you see light green filaments. This is the cosmic gas that condense in these filaments, and at the intersection of filaments where galaxies form. And these purple regions are really stars forming galaxies. When they form, they're blue, and as you will see, they age with time. These white dots instead are black holes that you just saw a couple of black holes. Oops, you saw right here another black hole popping out. We have implemented over the last few years models of black hole formation in cosmological simulation. So now we can really track or try to the formation and evolution of black holes in galaxies. Now you see here that in this cosmic evolution, as galaxies merge and interact, the black holes that they carry in their center also participate to mergers. Black holes don't necessarily merge as quickly as galaxies do. Sometimes they linger for a very long time. You see here, there are 3 black holes in this galaxy, 1 black hole here. This is a poor stranded black hole that probably will not do much in its life, except orbiting towards the outskirts of the galaxy, although it may get lucky and eventually be dragged to the center. You see that it has a very nice eccentric orbit. But so through this combination of growth of black holes as they create gas from the galaxy. Now you cannot see this here because black holes are extremely tiny, have a physical size. You think of the event horizon of microparsecs. And this box is several tens of kiloparsecs, so you cannot see the growth in mass of black holes, but you can see that they really participate to this whole cosmic evolution. And you can see here what we call the cosmic dance of black holes that try to get to the center of a galaxy and eventually merge with the central black hole. So here we have seen about 13 billion years of evolution. We have finished with a galaxy slightly less massive than the Milky Way. You see its stellar bulge in the center with the old red stars, but also you see a galactic disk composed of gas and younger stars. So in agreement with what we see in observations. Now, what we want is to link this cosmic evolution to observations, as I said, in different wavelengths. This is kind of standard in astronomy, but also with this new messenger, this is gravitational waves. This is just a very quick primer on gravitational wave observations. I don't do data analysis or technology. It's really to give a sense of why we need different gravitational wave detectors. In the same way that we have light at different wavelengths and we need to build different type of telescopes to detect it, it's the same with gravitational waves, which are characterized by a frequency. For the merger of two compact objects, for instance, two black holes, you can approximate the frequency at which they merge as the speed at which they move divided by the separation. So two black holes merge when they are roughly separated by their respective Fortian radii, which is here at the bottom, and the speed is close to the speed of light. So in this simple Newtonian approximation, which is actually obviously not reality, but it's a simple approximation, since the Schwarzschild radius only depends on the black hole mass and constants, you see that the frequency at which two black holes merge will be inversely proportional to the mass of the black holes themselves. Now, for objects with mass comparable to stellar mass, we are at high, for me, it's high frequency. So comparable to what LIGO, Virgo, Cagra are observing at this time. But if you go to more massive black holes, the frequency decreases. For instance, for a million solar mass binary, you get to about millihertz. And for a billion solar mass binary, you get to micro to nanohertz. So you need different instruments, and in particular, since the gravitational waves are detected through the stretching of space-time by using interferometry, you need an interferometer which has a size comparable to the wavelength that you are trying to detect. Low frequency means long wavelengths. So in practice, the instruments to detect low frequency gravitational waves don't fit on Earth. So you have to go to space. In fact, LISA is a satellite with an arm length of about 2.5 million kilometers. While to detect even larger black holes, so to go to nanohertz, we cannot, at the moment, even build an instrument. And so there is a very clever experiment called Pulsar Timing Arrays that uses the whole galaxy, or better say, the distribution of pulsars in the whole galaxy, to time whether gravitational waves are passing through our space-time. In the same way that these gravitational waves move space-time, they change the time of arrival of pulses from pulsars, and this is the way this is detected. Of course, in reality, this is much more complicated, but it gives you a bit of a feeling of the type of instruments that you need, that we need and want. So what is the main reason why we think that the combination of gravitational waves and telescopes is really necessary to constrain black hole evolution? This is shown in this figure, which is taken from the LISA science case. Again, the redshift mass plane. Again, this shaded area shows the reach of LISA. This gray area shows the reach of the electromagnetic of telescopes, basically. At the bottom right, I've added also pulsar timing arrays that, as I said, focus on massive black holes at only at low redshift. But superimposed here, you see 4 tracks of different colors, which are the evolutionary tracks of massive black holes in a theoretical model. So you see here black holes at some point form with either low or higher mass. This is a very, very massive SID. Of course, you can ask me more about this. I'm not going to go into detail in this talk. And after formation, these black holes grow by gas accretion. You see that they grow by gas accretion where their mass increases smoothly like this. But also when you see jumps in the mass and you see a circle, this is when a black hole merger has happened. So really through this combination, whenever you have a black hole merger, you have an emission of gravitational waves. Whenever you have a smooth evolution by gas accretion, you have emission of photons, and so something we can detect with telescopes. So you really can see that through this combination, we can see the 2 salient phases of black hole growth, either by merging with another black hole or by accreting gas and thus emitting light. So as black holes grow over time, they sweep the LISA band, then they enter the realm of our telescopes, and eventually the most massive of those can even contribute to the signal that pulsar timing arrays can detect. So really this full combination is a very powerful tool to track the growth of black holes over time. However, it is not as simple as I made it look. The research in the field of massive black hole mergers and dynamics started in 1980 with a seminal paper by Beagle, Blanford, and Rees. They were the first that asked, so what happens if, this was really seminal in the sense that we had just discovered quasars. So we know that black holes are in the center of galaxies. And they went a step further and said, okay, if two galaxies host black holes and the black holes are in the center, what happens to these two black holes? Do they merge or not? Well, the answer is still being looked for right now, although we have made some progress in the last 40-something years. But it's a very complex problem for many reasons, and in particular because it is truly a multi-scale problem. So if we want to understand just the merger rate of galaxies, and since galaxies host black holes, the merger rate of black holes will be modulated by the merger rate of galaxies, we have to go on cosmological scales. It's really, the initial conditions after inflation that determine where galaxies form with which power spectrum. So the timing of galaxy mergers is all encoded in the initial conditions of cosmological scales. So you need to simulate with different techniques, with analytical, cosmological simulations or analytical models, scales of hundreds of megaparsecs. Then if you take the merger of two galaxies there, then there is the physics of the galaxy merger itself. This is shown with very quick movie, but in reality, the merger of two galaxies lasts for several hundred omega years or up to 1 billion years. It's driven mostly by gravity, but you have a concomitant effect that change the star formation rate of these galaxies, for instance, trigger AGN and so on and so forth. If all goes well on these scales, a process called dynamical friction helps the black holes to lose angular momentum and energy, and slowly or fast, depending on their orbits, decay towards the center of the merger remnant. Until on scales of about parsecs, a few parsecs, this depends on the black hole mass, so it's larger for larger black holes and smaller for smaller black holes, they form a bound binary. At this point, the type of physics at play changes. It's not dynamical friction anymore, but it's interaction with other individual stars, stellar scattering. This is called stellar hardening. Gas stars, so interactions with, for instance, a circumbinary disk, in analogy very much with circumstellar or circumstellar disks and planets migrating in these disks. And also three-body interactions. If you have multiple black holes, the three of them can interact and exchange energy and momentum, and also have go through effects such as the quasi-Dirac mechanism, or even just change eccentricity. Eventually, if all these processes can take the binary from about parsec scale to milliparsec scale or beyond, the black holes can start emitting gravitational waves in an efficient way and eventually merge. So these are all the physical processes in one slide that we have to study and understand if we want to model black hole dynamics in a cosmological context. And something that was realized relatively early and was quantified more recently is that even if two galaxies, each hosting a black hole, merge, the formation of the black hole binary and its coalescence are not guaranteed. This was already present in Bigerman Blanford Arrays 1980. They went through analytical calculations, and later on, with simulations, we were able to try and estimate how often a galaxy merger leads to at least the formation of a pair of black holes in the galaxy center. I'm not even talking of a binary here. It's just two black holes that are a separation of a few hundred parsecs before the formation of the binary. And this table reports the success rate as a function of the mass ratio of the two merging galaxies and the mass of the most massive galaxy. So the color coding and the fractions written here is the fraction of galaxy mergers that lead to a formation of a black hole pair. And you see that it can be at most about 75% for relatively massive galaxies with very similar mass ratios. In fact, as you go to low mass ratios, you see here that the fraction becomes very small, sometimes compatible with the null fraction. And in this case, it's because the secondary small galaxy, it tends to be destroyed, disrupted as it moves in the deep potential well of the most massive galaxy. So in general, we already know that if you have 100% of galaxy mergers, the number of black holes that you get from this must be lower than about 75%. Besides just the probability of eventually pairing, the evolutionary timescales is just much longer than the evolution of the galaxy, because as I showed you in the previous slide, you have additional physical processes. So basically, two galaxies merge when they when they reach about kiloparsec separation. They have a few pericenter, and they merge together. But black holes don't merge at kiloparsec scales, but at milli to microparsec scales. So this is why you need these additional delays. So as I mentioned, when the mass ratio of the merging galaxy is close to unity, the merger time scale is short. And for short, I mean hundreds of millions of years to about a giga-year. When the masses are very unequal, the secondary galaxy tends to be disrupted depending on the orbit, and it leaves behind a black hole that at this point is in the potential well of the main galaxy, but it's not attached to the other galaxy, and it's not on its way to the center. It's just that its dynamics is very inefficient. And so we're left with the prediction, and this is a very strong prediction that dates back to early 2000. Even in my PhD, I had that there is a population of wandering black holes, so black holes that have not made it to the center. In some cases, for instance, for this galaxy here, the galaxy merger happens very fast, and the black hole merger also happens very fast. You see here that in less than 300 million years, you go from two separate galaxies over here to a single galaxy with a single black hole in the center. This is facilitated by the secondary galaxy having a very compact appearance. In this case, which has a similar mass ratio, but the galaxy is more puffed up, after almost 2 billion years, you still haven't formed a binary in the center, and the secondary black hole is still out there. Now, if you repeat this over a number of mergers that you have in the universe, and you take a galaxy like the Milky Way, you can see here that you're left with not only one black hole in the center, which is here and you see it, but also with a bunch, usually a few. For a Milky Way, it's something like a few. In this case, it's 1, 2, 3, 4, 5 wandering black holes that are just hanging out there. Their orbits are not conducive to getting to the center. The galaxy that they were hosted in the beginning has been disrupted. So really, they are kind of point masses with very small cross sections traveling through the outer region of the galaxy. Of course, you can ask me more about them, but I can mention that they are extremely hard to detect, although we have some candidates that could be wandering black holes. I'm sorry. The main process behind this early phase evolution is a process called dynamical friction. I already mentioned this. In physical terms, this was discovered by Chandrasekhar several decades ago, and it really it was developed to describe the motion of a particle in a homogeneous distribution of other particles. And if the moving particle is massive and so that it can be distinguished from the background, you can calculate that the forces acting on on the surrounding stars are not canceling out in the radial direction, although they're canceling out in the tangential direction. It's simply that if you have a preferential direction for this black hole, you will be left with some leftover force in the radial direction. This manifests also in an accumulation of particles, in this case stars, in what is called a wake. You see here it's an overdensity just behind the black hole that acts as a sort of a drag, slowing down the motion of the black hole. As I said, so this is reported from Chandrasekhar. This is a slide that I borrowed from Ugo Pfister. And you see that the deceleration of the massive body, in our case a black hole, depends on local quantities such as the density, the distribution of stellar velocities, and the relative velocity between the black hole and the stars. Now, this is well understood physics, as said, developed by Chandrasekhar way long ago, but it has challenges when you try to study this in a cosmological context, especially in the case both with semi-analytical and numerical simulations. Let me start with numerical simulations. So the effect of this dynamical friction depends on your ability to actually track the motion of these stars forming this wake. The size of this wake is very small, it's about parsec scale for this parameter shown here. And in most cosmological simulations, it's very hard to resolve sub-parsec scales. So we are, in general, unable to calculate correctly this force. So instead of having a wake forming there, you just have a small, very tiny global overdensity. So we're not really able to resolve the force correctly. And this means that in most cosmological simulations that have a resolution of 0.1 to 1 kiloparsec, instead of 0.1 to 1 parsec, we are missing the correct force. Historically, there have been two approaches to this. Historically, the first one was for the advect massive black holes to a minimum potential well. So you literally take the black hole and you move it, or to account for the missing force, this dynamical friction, and you can do it by calculating the actual force that you expect from all the particles in your sub-parsec region. So again, it's fully based on the formulation by Chandrasekhar, and you just have to implement this nice integral in your simulation. Now, if you include this dynamical friction, this new force, then you see that the cause behave dynamically more naturally. So this is something that was done by Michael Tremel, Ugo Pfister, and also by Johan Dubois, including gas dynamical friction. This is based instead of Chandrasekhar on Stryker 99 formulas. But so the point is that at this point we have a series of simulations that include this new physics that allows us to track the evolution of black holes. And this is where I had a very nice surprise. Well, I'm not sure if nice is the right word, but I certainly was surprised. Because earlier on, so when I started working on this, again, in early 2000, during my PhD, I was using analytical and semi-analytical models. So what I was doing was simply to integrate the dynamical friction deceleration from Chandrasekhar. And if you go to Bin and Tremaine, well, they very conveniently have done it for you. If you have a nice potential, such as an isothermal sphere, this becomes a fully analytical solution. And you see here, if you have an object, in our case, again, a black hole, starting here in this position of a galaxy, you can calculate the time it takes for it to reach the center. Depends on this initial separation, the velocity dispersion of stars in the galaxies, the inverse of the black hole mass, and this is it's a Coulomb logarithm, is never well defined in the literature, but it's a number that it's a logarithmic number, so it's not particularly, it doesn't change more than an order of magnitude. So we're all very happy, for 20 years, we calculated these dynamical friction time scales, the merger time scales. But then we have included these dynamical friction simulations, and we had, as I said, some surprises. The point is that here you see, we are modeling this evolution in a nice smooth galaxy. And this formula is, also assumes a nice potential like an isothermal sphere. But turns out that when you look at actual high redshift galaxies, they're not very nice, relaxed galaxies. So especially if you go to high redshift dwarf galaxies, you really have something that resembles a collection of clumps. On top of this, just the shallow potential well is such that the black holes can kind of move around, like if you have a very large ball and you have some balls and you can play with them, and you see that they don't reach the center because there is no center of potential well. So instead of having black holes just nicely going down to the center, having no center, you have these black holes just moving around in a what we call an erratic way. And depending on the mass of the black hole, so this is exactly the same simulation. We only changed the black hole mass, 10^4 and 10^5 solar masses. You see that is a light black hole. So you see here the dependence of the black hole mass to the -1 that remains in all equations. A massive black hole kind of wanders around, at the distance of about a few hundred parsec from the center, so about the size of the galaxy. But if you have a light black hole, it can just really go away and never come back. So these erratic dynamics really changed our picture of how we have to understand black hole dynamics, adding a very strong stochastic factor that we have to account for. So now this means that, at least in my case, I decided recently to focus on using cosmological simulations for our studies. And this, however, led me to a sort of conundrum, because when we want to simulate, we want to run cosmological simulations, we are faced with a choice. If you're an observer, it's the same for surveys. We can either sample the large scale structure, so have a large volume simulation. And in this case, since you sample a large volume, you also have many galaxies. But you also want to resolve small physical scales. I told you that all the physics important here is on scales smaller than 1 kiloparsec down to less than a parsec. So you want to have high resolution. Finally, if you want, like me, to study both black holes for LIS and pulsar timing arrays, you need high massive black holes in massive galaxies for pulsar timing arrays, and low mass black holes that inhabit in dwarf galaxies for LIS. And this is just simple. As I said, there is a correlation between black hole mass and galaxy mass. So if you have high mass black holes, they will be in rare massive galaxies. And if you have low mass black holes, they will be in common but low mass dwarf galaxies. So at this point, you have to choose either to have a large volume, but low resolution simulation. This is, in observational terms, this will be a large and shallow survey, such as, for instance, SDSS, or a small and a high resolution, or deep in the case of observational survey, simulation. So the analog of a small and deep survey, something like the Hubble deep field or the Chandra deep field. They really have exactly the same pros and cons as observational fields. In a large, shallow survey, you have lots of massive galaxies, but you cannot resolve very well the low mass galaxies. And vice versa, if you have a small survey but very deep, you can go very, very high redshift, detect even dwarf galaxies at high redshift. But then you lose all the massive ones because they are too rare. So over the years, there have been many simulations, mostly focusing on the large volume, low resolution type. Here, there are some names. You probably have heard of Illustris, Eagle, Massive Black, and so on and so forth. The one that I use is called Horizon AGN. It's a large simulation in the sense that it has a volume, a size of 140 megaparsecs. This is a cube, so you have to cube that and you get the volume. I'm not going into the details, but you can ask me, specific details about the implementation of the physics. And of course, we have black holes there with their accretion and dynamics, or as best as we can do with a simulation that has a resolution of 1 kiloparsec. But then what we did recently was to take this horizon Aegean simulation, select a small sphere in a region, a very normal region of the universe, and then resimulate it at much, much higher resolution until we get to a resolution of about 40 parsecs. And in case you see, you can really resolve star-forming regions inside a given galaxy. So we can really see the details of galaxies in terms of the physics. We can resolve, for instance, thin disks and so on and so forth. Again, I'm not going into details in the physics here, but we have very, very, very good physics for black holes in particular, because that's something we wanted to have. So at this point, I have two simulations. As I said at the beginning, you have to choose either large and low resolution or small and high resolution. But since I had two simulations, I could combine the two to get a view of both massive black holes with the large simulation of Horizon Aegean and small black holes in the smaller simulation, New Horizon, that resolves dwarf galaxies. And you see here, after effect of my analysis, if I look at the merger of black holes, the distribution of masses for black hole mergers from the two simulations, New Horizon and Horizon Aegean, you see that indeed they cover the expected range for both LISA and Pulsar Timing Arrays. So they don't combine the two missions, and also the simulations only barely overlap here. But at least we have a sample where we can test our physics. So this is a sample that I used to study the evolution of black hole mergers in the universe with these simulations. But as I mentioned, these simulations have a finite resolution. In the case of Horizon Aegean, it's 1 kiloparsec. So 1 kiloparsec is around here before the formation of the binary. New Horizon, the high resolution simulation, does better. It has a resolution of 35 parsecs. So we really get, kind of to this phase. But still, it's not enough to resolve these physics on smaller scales. So I still had to add some additional physics. Now, simulations like this take 2 to 3 years to run. It's a very long way. So I couldn't rerun the simulations, but what I could do is in post-processing, take the results of the simulations and calculate all these additional processes that happen under resolution. And this is exactly what one can do. At this point, you have to use analytical solutions. So you have to make some simplifications, but you can estimate some delay time scales between when the simulation tells you that black holes merge on kiloparsec to hundreds of parsec scales to when the black holes actually merge on microparsec scales. So I calculated these delays. And here, I don't want to go into details. You can ask more, of course. But what I want to highlight here is that this is the calculation of these delays in log scale. This green line shows the Hubble time today. And so you can have very short delays. In some cases extremely short, but you can have delays that are 6 orders of magnitude, well, 4 or 5 orders of magnitude larger than the Hubble time. So including these delays means, once again, that not all galaxy mergers lead to a black hole merger, because you have to consider that between the galaxy merger and the black hole merger, you can have 10 to the 6 billion years, which is a bit in the future for now. And probably with dark energy, that would make things even worse. So I took this sample and calculated the merger rate for black holes. Now here, just focus on these black curves. This just shows that the changes that adding the delays make. This is without delays, and then adding more and more refined delays, you get to the black curve. This is for the two simulations. Horizon Aegean, once again, is the large volume, low resolution. New Horizon is the high resolution, small simulation. You see immediately that in the small simulation, you have many, many more mergers than in the big one. But new horizon is just a resimulation of the same, as a subvolume, an average subvolume of horizon HN. But if you have a high resolution simulation, what comes in is that actually you start to resolve dwarf galaxies. And in the universe, dwarf galaxies dominate the universe. If you go to the galaxy mass function shown here for the hypersuprime cam, and for New Horizon as well, to show you that there is a good match between theory and observations, you see that the number of galaxies as a function of galaxy mass increases at the low mass n. So here we have the stellar mass. Below 10 to 9 solar masses, we are in the realm of dwarf galaxies that clearly dominate over the massive galaxies that are, like the Milky Way or so. So once you have a simulation that brings you from resolving galaxies with 10 to 10 solar masses to resolving galaxies with 10 to 7 solar masses, your number of galaxies greatly increases. This is classic. We have known this forever. But what I showed you is that there is not only an increase in galaxy numbers, but also in the number of black hole mergers. This means that a significant fraction of low mass galaxies, of dwarf galaxies, actually host black holes. For instance, theoretically, in our simulation at redshift 0.5, about 10% of galaxies with million solar masses and stellar mass host a black hole. And all galaxies with a mass of 10 to 9 solar masses host a black hole. So this is shown, that this is our theoretical expectation, but as you see here from observations, this also seems a reasonable result in the sense that indeed we expect the presence of black holes also in dwarf galaxies. So if you have many dwarf galaxies, you have many dwarf galaxy mergers, and it follows that at least a fraction of these dwarf galaxies with black holes may lead to a black hole merger. Although, as I showed you, dynamics is complicated. So the first point to retain is that if you want to make predictions for black hole mergers, especially for LISA that sees black holes with mass 10 to the 4 to 10 to 7 solar masses, you really need to include dwarf galaxies in your model. If you only include massive galaxies, your models are very appropriate for pulsar timing arrays. But if you're a LISA person, you have to love dwarf galaxies. Another question that several people asked me over the years, and I was finally able to touch on, is are merging black holes found in merging galaxies? The expectation of you have to merge in galaxies, then you will see merging black holes in there. Well, unfortunately, this is not the case. In general, these delays between the galaxy merger and the black hole merger, this is the time dilation here in gigayears, in billion of years, as a function of galaxy mass, can be in some cases tens of gigayears, a few gigayears to a few tens of gigayears. So this means that between the time when the two galaxies merge and the black holes merge, the galaxy has changed considerably. Has changed its mass, it's changed its star formation rate. It may have experienced mergers, but it's not the same merger that led the black holes, and this happened years ago. Let me show you here some examples. So here we are following the evolution of two black holes. Here, their evolution started at redshift 3.18 when the universe was 2 billion years old. You see here these red circles highlighted two black holes in this interaction between three galaxies. And the two galaxies hosting black holes have masses of about 10 to 9, 10 to 10 solar masses. To find the time when the two black holes form a binary, we have to move forward in time by more than 2 billion years, 2.5 billion years. And by that time, the galaxy has changed considerably. It has become a very massive diskish galaxy, still very dusty. But then if you look at the time when the black holes merge, this is again after more than 3.5 billion years later, at this point, the galaxy is a nice relaxed disk, dusty, but nice and relaxed. So nothing in this galaxy makes you think of a train wreck like the merger that happened 6 billion years before. So when we look for black hole mergers, massive black hole mergers, we don't necessarily have to look in disturbed galaxies. This is not necessarily always true. This is an example, at the other extreme. This is a high redshift merger, black hole merger and galaxy merger. It started at redshift about 7.5 or so. when the universe was really very young, less than 1 billion years old. You see these two black holes hosted in two very dwarf, high-redshift, massive galaxies. The two black holes find each other, so meaning that they form a pair. Shortly afterwards, only about 200 million years later, and eventually they merge, well, 2 billion years after this, but still when the universe was very young. You see here at redshift 2.5 or so. In the high redshift universe, galaxy mergers are extremely common. So although there were 2 billion years, about 2 billion years between this image and this, it's not that this galaxy is still disturbed because of this early merger. It's just that this galaxy keeps on experiencing mergers. And also here you are finding a black hole merger in a disturbed galaxy. But in this case, it's not necessarily because of this very early merger. So this, again, is something to be kept in mind when looking for black hole mergers in using our telescopes. How can we find binary black holes? So I mentioned, you just want to find merging black holes. We don't have LISA yet. So how can we use electromagnetic waves to find it? Well, over the years, many people have studied this process. And interestingly, they found some signatures. Now, the type of physical environment that we can imagine is something like this. So you have a distribution of gas. This is called the circumbinary disk. You always have angular momentum in the universe, so the gas will be rotating. So that's why you have a circumbinary disk. You have two black holes in here. Forget this black circle in the center is just an artifact of the space-time. And these two black holes, as they evolve in this gas configuration, exert torques on the surroundings. And so they acquire what we call the mini disks. So each black hole has its own small accretion disk, all embedded in a larger circumbinary disk. So it's a pumped up accretion disk, in which you have also features such as gaps. These gaps are created by the exchange of angular momentum. When the viscosity is not efficient enough to dissipate this angular momentum. And we also have streams of gas connecting these circumbinary disks to these mini disks. So this is a very rich physical picture. And you also have lots of gas near black holes. If you have gas and black holes, typically have some activity, some of the gas crosses. So these accretion disks will be luminous. You have a binary system, so you expect some periodicities in the light curve. You can expect double peaked emission line profiles, again, because you have Doppler shift caused by binary motion. So one will be a timing issue. The second will be a spectroscopic confirmation. You can have gaps in the accretion disk spectrum. So if you're familiar with the Schoenberg solution, in an accretion disk, you can approximate the emission from the black hole going farther out as a series of black bodies with decreasing temperatures. But if you have a gap like this, you truncate or you miss the light from the frequencies of the black body that would correspond to these holes in the actual disk. And so you expect some gaps in the spectrums that are sometimes called notches. And also when these streams from the circumbinary disk hit the mini disk, you expect shocks that emit in hard X-rays. So you have this wealth of information. And then what has been done using cosmological simulation, see how often or how many binaries can we expect to detect through these techniques nowadays, using our telescopes, or also thinking of using the LSST survey with the Rubin telescope, which is a timing survey. And the answer is that as long as we focus on, so here there is a bit of a trade-off again. So we have either the massive black holes that are very bright, so they can be picked up in many surveys, or we have the faint black holes for LISA that usually are below the sensitivity limit for most surveys. So in these works, we have focused mostly on massive black holes, those for pulsar timing arrays, but it can also be observed in something like SDSS-5 or in LSST on Rubin. And if you calculate how many you see, really it's not that many. It's a few over the sky, but this is consistent with the limit and possible detection from pulsar timing arrays. So it's a complex problem, but again, we have the hope to detecting a few tenths of this in the next few years. And then this will tell a lot about the environment about black holes, around black holes, and whether our calculations for the dynamics was correct. Now, in the last few minutes, probably 3 or 4 minutes, hopefully, I will take a small step back. So here I talked about binaries. Really black holes that are separated by less than a parsec, something like 10 to the 4 Schwarzschild radii. But we also have the hope to find black holes in an intermediate stage when they're separated by kiloparsecs. This is what we call dual AGN. Now, if you look at black holes separated by a few kiloparsecs, it's much harder to predict whether they actually merge or not. But it's much easier to find this type of dual AGN in the sky. In fact, the first was detected in 2003, Comas et al. You see here Hubble and the X-ray image that really showed this 2 AGN buried in the center of this very much obscured galaxy. They're separated by a kiloparsec scale or so. Then later on, many more were detected, and now we have a substantial set of candidate dual AGN. But these dual AGN are not observed only in the sky, they are also produced in simulations. And again, over the years, many groups, including my group, have worked on trying to predict the properties of this dual AGN. So you see here some examples. This is a dual AGN. So these are 2 AGN active in the same galaxy. So something like the galaxy I showed you earlier here. These are 2 AGN in a train wreck, a merger at high redshift. And this is my favorite, is a quadruple system 1, 2, 3, 4 at much higher redshift. So here the crosses show just chance superpositions projected on the sky. But we have actually some that are physically linked. And so may or may not, but I will show it in a minute, lead to black hole mergers. So when I study dual AGN, usually or at least I decided to follow this train of thoughts and to choose dual AGN that can be observed, going back here, either in the same galaxy. So there are 2 AGN in the same galaxy, so the same shown here, or you can have multiple dual or multiple AGN observed in multiple galaxies, like in this case. So we did the same analysis. So we selected either multiple AGN that are hosted in the same galaxy, the example is shown here in orange, or dual AGN that are still in 2 separate galaxies. So if we follow here, this is the separation of the 2 black holes over time. For 2 black holes that are in the same galaxy, they started far away in 2 galaxies very far away. You see here, the distance is hundreds of kiloparsecs. Then at some point, the 2 galaxies become bound. They start their dance of aquant pericenters. The galaxy merger happens around the time when we observe them. So we observe 2 black holes in the same galaxy. Sorry. Yeah, these are, I messed up these 2 arrows. So the 2 AGN in the same galaxy is the green one. So you have the galaxy merger happening earlier. So the 2 galaxies have already made one in this case. And when you observe the 2 black holes at this redshift, they are in the same galaxy. Vice versa for dual AGN observed in different galaxies, the observation of the dual AGN happens before the galaxy merger. And in the bottom, you just see the growth in mass of the 2 black holes over time. Now, the point about the dual AGN is not that you see just black holes, but they're active, so they're accreting, they're growing in mass. So you have to catch them in a phase in which both black holes are active, which is not always the case, meaning that black holes during their evolution sometimes are on, sometimes are off. Not all quiescent black holes are active. So we have the Milky Way black hole, which is an example of an inactive black hole that would not make a dual AGN. So then you take all these simulated dual AGN in different galaxies. So two black holes separated in two separate galaxies. This is shown in gray. Or two dual AGN, a dual AGN, sorry, where the two AGN are in the same galaxy, and this is shown with this pinkish color. And then you can ask, just let me focus here on the right-hand side, which fraction of the dual AGN I see can I track in the simulation to an actual black hole merger? So I showed you earlier, with another simulation that about 75% of galaxy mergers at most 75% of galaxy mergers can lead to a black hole merger. So on average, this will be, even less than that. Now, if you have dual AGN, you know that both galaxies host black holes, so this already increases the probability. And in fact, if you look for a dual AGN hosted in different galaxies, you find that about 80% of dual AGN mark the location where eventually a black hole merger will happen. This probability is slightly higher, shown here again in pink, if you select dual AGN that are in the same galaxy, because at this point, the two black holes are already have already traveled a little bit of their journey. Unfortunately, when you add these post-process delays, as I said, the simulations cannot track self-consistent in the old growth of black holes. We have to add these delays that can be up to 10 billion years or 10 to 6 billion years if sometimes you consider them. This fraction decreases significantly. So only about 30 to 60% of dual AGN will eventually result in a black hole merger. So you can use dual AGN to make inferences about how many black hole mergers we have in the universe, but we have to adopt corrections and modify our predictions to take into account the inefficiency of black hole dynamics. So this leads me basically to the end. I hope that I just convinced you that the field of massive black hole evolution is really rich in physics, rich both in theory and also in observations as shown here. Much of this space will be opened with various observatories in the next few years. The only other point that I want to make is really that 20 years ago, we thought that black hole dynamics was difficult, but at least this could be described by simple analytical formulas. But now we have discovered that stochastic effects make our life even more complicated, but it's still a great field where to work on. And I will stop here. Thank you very much.
Thank you very much, Marta, for this very interesting talk. And I think that there are going to be questions. We don't have too much time, but please feel free to ask the questions and mute yourself, or if you cannot speak, you can write them in the chat. So, yes, don't be shy.
And I'm sorry for having gone over time.
No, it's fine. I mean, there's not a hard limit. Okay, I might ask one question. I mean, I'm not working in this field, but I was kind of intrigued about the mini disks that you discussed in this merging, in these dual black holes, around dual black holes. And I was wondering, you said that some of them could be discovered by a gap or a decrease in the UV spectra, and some of them would be seen by E Rosita in X-rays, but I didn't quite understand what is the origin of the X-rays in this case. If you could explain a little bit more.
Yes, the origin is shock. So this the gas from the circumbinary disk. So this gas over here, sorry, it's a bit small indeed. But you see here these streams of gas that leave the circumbinary disk and join the accretion disk. So these are supersonic streams, and therefore when they hit the mini disk, they create a shock. Very high temperatures that in principle should be observable in X-rays.
Okay, I see. And okay, so these would not be necessarily acting as, I don't know. So this would act as an AGN, meaning disaccreting black holes? Because if they are, I was wondering how can you distinguish them with respect to the actual X-ray emitting AGN?
Exactly. No, this is of course a very good point. So the hope is that the shape of the spectrum is different, so that you have a shock instead of instead of the standard power law that you see in AGN, you have a different shape. The other hope is that this. Sorry, let me go here. The other hope is that perhaps this happens periodically. So if you observe a source, a source over a few years, you see these shocks coming up. But touched on a very subtle point. Most of these predictions could be easily confused with other things. For instance, just variability in AGN. Most of the candidates have been ruled out because, they thought it was periodic, but no, they're just variable. The emission line profiles also have can be created by the double peaked emission line profiles can be created by lopsided disks. So yes, I've been kind of cheating a little.
Okay, so maybe and the gravitational wave signal from that.
Okay, if you get a joint detection, then you're safe.
Okay,
but that will have to wait a few more years.
Yes, in the future. So I see one question in the chat by Marcos Polkas. He's muted. So he says, disregarding stellar mass and redshift dependence, I would like to know from simulations and observations, what's an upper limit on the fraction of binaries amongst AGN?
So this was, there was a nice paper probably 10 years ago or more, probably 15 years ago, by Barzon and Lauer, who used this spectroscopic technique of finding Doppler modified lines, so either two lines or one weird line, to put a lower limit or a limit on the binaries, and the results was consistent with 0. Then I went and calculated the same in my models, and my results were consistent with 0 as well. So at the moment, I think that we are still, so since then, there have been some improvement. And so now we have few candidates, but I would say that over the whole sky, based on current observations, observationally, we have a few candidates, less than 10 for binaries. And here I really mean binary systems at separations of subparsec, 10 to a 4 shear radii and less. And from observations, we also expect, a few over the entire sky. So at the moment, it's consistent. It's not large numbers, but we're hoping with deeper surveys and higher resolution simulations to improve. I think that the bottleneck here is really the current large sky surveys are relatively shallow. So you cannot see the small black holes that dominate them numbers.
Okay. So Marco, if you want to ask more, or
but here it was about the fraction. The fraction. I think it's in this paper by Cézanne et al. I think that they express this as a fraction. There could be something also in this, but it's less. It's less than 10 to the minus 3 that I remember.
Okay. Yes, so there have been also some claims about having like binary massive black holes in AGN with jets. They have been looking for some quasi-periodicity in gamma rays, and also by looking at the radio imaging, let's say, of the large jets. So what is your take on that? Do you really believe that these are secure identifications of binary black holes?
No, the only secure one is one found by Rodriguez et al. With a separation of a few parsecs. In the case, you please clearly see the two the compact cores. But for the others, I'm afraid that they're all still candidates. OJ287 is, the poster child.
Yeah.
Everything works, but it's just that in that case, you have a very bizarre binary, extremely massive. So you're always wondering a little bit about that.
Yes. And if I may ask one more question, if there are not other questions, but feel free to ask Marta. I was wondering, because perhaps you mentioned it, but I didn't quite catch it. What is the mass ratio of these binary black holes that you see in the simulations, at least, whenever you see like the formation of a binary system?
So the typical mass ratio is about 10%, 0.1, 1 to 10. The reason is that mass ratios with mass similar to 1, so 0.1 and higher, are very rare in the universe. Vice versa, those with a very unequal mass ratio, usually then they have a very inefficient dynamics, so they don't actually merge.
I see.
So the two combine to give a peak at about 0.1. Give it or take a few.
Okay. Yes, let's see if there are any hands raised. I see one hand raised. Yes, Apostolos Mystichiadis.
Hello, thank you very much for your talk. Too much new information for me. We have a problem understanding lone AGNs, let alone double or twin AGNs. But I have a question concerning you talked about it, but still I have some questions. The resolution of your simulations. You seem to have lots of your results based on the simulation, on this resolution. So my question is, how you expect the increase of the resolution in the next years to improve your findings or change your findings, for one thing? And the second thing is, are there, since you have many, you say that you have many physical processes, are there really any important physical processes missing from the simulation you're talking? You talked about cooling, you talked about supernova feedback or whatever, but are there other that you think that could be crucial? I'm talking about because I see the history in the field, and I know that by improving the resolution and putting new physical processes or neglected physical processes, things change over the years. So my question is concerning this point, basically.
Yeah. So first, I'm not a simulator who says that simulations, solve everything and they're always right. Partly because I came to simulations from analytical work, so I'm always a bit skeptical. They're very helpful because they can follow nonlinear processes. So that's and they make pretty movies. But so in terms of resolution first, because this is a bit faster. Saying that we resolve the bare minimum processes is the best I can say. So even star formation is put in kind of by hand in the same way. You have the Koenig-Schmidt relationship, and I think that it's safe, secure from observations. But when you go to high resolution, you cannot use it anymore. So you have to use new tricks, but you still don't resolve dense molecular clouds. It's the same for black holes. In many cases, we're making approximations that may or may not be correct. So you can only hope that there will be improvement rather than changes, but I'm totally open to having changes. That's something that I expect. For my specific field, I think that, for instance, for the moment, in simulations, we don't have at all the binaries. The feedback is put by hand. So I think that feedback could be a main change in the way binaries evolve as well, for instance. And we don't have anything on scales below 10 parsecs, which is where the crucial physical processes happen. So I would take these as, I think to me, these simulations are an indication. They were very, very helpful in finding processes that we could not discover with analytical techniques. So for instance, all these stochastic effects, now we know that we have to include them, but I don't think that we have a distribution that we can say, we Monte Carlo on these effects and we get the right results. We just know that they are there and they're a nuisance in some sense, or more exciting. In terms of the physical processes, I already mentioned feedback. I think that's one thing. The actual evolution of binaries is, I think, one of the key points. So at the moment, we're mostly assuming in post-processing circular or semicircular orbits. Not guaranteed. Actually, what we expect is that most orbits will be eccentric. It's just that an eccentric orbit is harder to model. So some of these are just shortcuts. You take a circular orbit, everything is, you can integrate, so you use it. So I expect significant changes. But as I said, I worked on this for 20 years at this point. I've seen from analytical models, semi-analytical models, simulations. And there are some things that, if you find the same result with 3 different techniques, I think it's robust. You may be completely missing something, but in general, for instance, this mass ratios of 0.1, you can understand it from first principles. So when you find it, it makes sense. Other thing, also the delays that they're about up to a billion years, again, it's something that many different lines of thoughts lead you to think of that. We could be wrong. I hope that we're wrong, because if we're wrong, we have many more black hole mergers in the universe and our life will be easier. So right now, I think, the way I describe my situation now is that I feel that there are too many things that we don't know. We are very pessimistic with the predictions. But I sincerely hope that it's because of the shortcomings in the models and the universe is smarter than us.
Okay, thank you. And thanks again for your talk.
Thank you.
Yes, thank you, Marta. I don't see any other hands raised. Yes, it was a very interesting talk. And I think that people are going to watch it afterwards anyway on YouTube. Yes.
Well, I hope they will not be too bored.
No, also Calliope will definitely watch your talk afterwards. So she will probably have questions.
Good. Okay. Thank you very much again.
Thank you very much for accepting our invitation. Bye.
Bye-bye. Have a good evening.